Okay, Giacomo will speaking on generalized strong subadditivity for Bosonic quantum system. Now, time is yours.
Okay, so first I would like to thank the organizer for giving me the opportunity of this talk. And here I will present recent results that I got in collaboration with Dario Trevisan from Pisa and Lucas Hack from Melbourne. And this result is about generalization. What? Sorry, I can't hear you.
You have to turn off your quantum. Okay, I think
this result is about a generalization of the celebrated strong subadditivity inequality for the von Neumann entropy. So, like this result concerns bosonic quantum systems. So, let me start with presenting what a bosonic quantum system is. A bosonic quantum system is roughly a system made of a given number that we will call M of harmonic oscillators. And we will call each of these oscillator a mode. And so, like, to each oscillator, we can associate the quadrature operator, that if the oscillator is like a physical particle, will be the position and momentum operators, labeled with Q and P. And each of the quadratures has each mode has its Q and its P. And as you probably all know, the quadrature satisfy the canonical commutation relations, that is, the commutator between a Q and the corresponding P is proportional to I times the identity operator. Then sometimes it's easier if we have all the position momentum on a common footing. And sometimes it's useful to employ this common labeling of the Q's and P's operators. We will call them collectively quadratures, and we put them together in this vector of two M operators that we denote with R. So the odd components of R will be the Q operator, the position, while the even components of R will be the momenta. And of course, the components of this vector R will still satisfy the canonical commutation relations. And now this, that are inherited from the commutation relations of Q and P. And now these commutation relations are written in terms of this matrix that I will call delta M. So M stands for the number of modes. So here we have n modes. And this matrix, okay, of course, the quadrature associated to different modes commute, so this delta is block diagonal. And on each of the M blocks, we have this submatrix here, which just tells us that Q commuted with P is I, and P commuted with Q is, of course, minus I. Okay, then for the following of this talk, it will be important not only what a bosonic system is, but also what a subsystem of a bosonic system is. And roughly speaking, we will identify a subsystem of a bosonic quantum system as a subset of the quadratures. And more generally, we do not consider only like a subset of the original quadratures, but we consider a slightly more general definition of a subsystem, where each quadrature of the subsystem is given by a linear combination of the quadratures of the original system. So we will call R prime the quadratures of the subsystem. And here you can see in this equation that each R prime is given by a linear combination of the original quadratures R, where this linear combination is given by a matrix that here we will call M. Now, I didn't say anything yet about the commutation relations between this new primed quadrature in the subsystem. I will do it now. And we will consider these two cases. Like the first case is what we call a classical subsystem. That is the case where all the prime quadratures actually commute. And if they commute, this means that they can be measured all together. And that's why we call it a classical subsystem, because we can measure all the quadrature in the subsystem and get like actual numbers for these quadratures. And in terms of this matrix M, we can express this condition of commuting quadratures in this way. So M times the delta matrix of the global system times M transpose should be equal to 0. While the second case that we consider is the case of a fully quantum subsystem. And in this case, we will need an even number of quadratures. And also the primed quadrature should satisfy the same canonical commutation relation as the original bosonic system. So the commutator between the prime quadratures should still be given by this I times this matrix delta times the identity, but now just, of course, the matrix delta will be adapted to the size of the subsystem, and of course, the number of modes of the subsystem will be half of the number of quadratures. And here I forgot to say that we call the dimension of the subsystem the number of quadrature it's made of. Here it's n. And of course, if the subsystem has to be fully quantum and has to be even. So how we can express this in terms of this of the matrix M that defines the prime quadratures? This is expressed by this relation here. M times the full matrix delta for M modes of the original system times M transpose is equal to the new delta, that's the delta reduced to the size of the subsystem. Okay, so let me going. So you will probably be already familiar with the von Neumann entropy of a quantum state. So let rho be the density matrix associated to the state of a quantum system A. Here we do not need it to be a bosonic quantum system, it can be generic. The entropy, the von Neumann entropy of the system A in the state rho is equal to minus the trace of rho times the logarithm of rho. And then once we have defined the entropy of a quantum system, we can define a conditional version of the von Neumann entropy. So we say that the conditional entropy of the quantum system A conditioned on the quantum system B is equal to the global entropy of the joint quantum system AB minus the entropy of the system B on which we are conditioning. And actually, a fundamental property of the conditional von Neumann entropy is the strong subadditivity. And this is this inequality here. So here we have first, you can notice that all the entropies appearing in the inequality are conditioned on a quantum system C. And then here on the left-hand side, we have a joint quantum system AB. And this conditioned entropy of AB conditioned on C is always less or equal than the sum of the entropy of each subsystem conditioned on the quantum system C. So what we will see in the next part of this talk is a generalization of this strong subadditivity inequality that applies to bosonic quantum systems. Okay, so let me describe the setup of this generalization of the strong subadditivity. So we consider a boson, like now A is a bosonic quantum system with M modes. And then we consider a bunch of subsystems of A, and we label these subsystems A1, A2, up to AK. So K will be the number of subsystems that we consider. But now contrarily to what was happening in the previous slide, we do not require these subsystems to be they do not need to be A will not in general be the union, the joint of the subsystems, but these subsystems are allowed to be overlapping. So there may be quadratures that belong to more than one of the subsystems. And moreover, each of these subsystems can be either classical or quantum, so they can be all quantum subsystems, they can be all classical, or they some AI can be classical and some other AJ can be quantum. And then we call N1 up to Nk the dimensions of the subsystems that if I remind you that I defined the dimension of a bosonic subsystem as the number of quadratures that build this subsystem. And I remind you that each subsystem is defined by some rectangular matrix. We called this matrix M in the previous slide. And here we will naturally call M1 up to Mk all the matrices that define these subsystems A1 up to Ak. Then, as in the classical version of the strong subadditivity, we consider some conditioning quantum system B. And here I stress that B can be a generic quantum system and does not need to be a bosonic quantum system. And we will need to consider also some positive numbers, P1 up to Pk, that have to satisfy this scaling condition that more or less P1 times N1 plus Pk times Mk should be equal to twice the number of modes of the global system, and this is needed for technical reasons. So I can now state what is the strong subadditivity, this generalization of the strong subadditivity for bosonic quantum system. So given a quantum state rho of the joint system AB, we consider this quantity here. We consider the entropy of A conditioned on B on the state rho minus a linear combination of the entropy of the subsystems AI conditioned on B, always computed on the state rho. And these positive numbers that I introduced before, these PIs are exactly the coefficients of this linear combination. And we call this function Fp of rho. And now we will be interested in the maximum of this function over all the possible quantum states rho. So if you compare this that problem with the original strong subadditivity, we can see that the inequality has the same form, we always are looking for the maximum of the entropy of the total system minus some linear combination of entropies of subsystems. The difference is that in the standard setup of the strong subadditivity, the subsystems are disjoint and their union builds up is equal to the global system, while in this generalized version, the subsystems do not need to be disjoint, and of course, their union does not need to be the global system. So we can have here much more freedom in the choice of the subsystems. And furthermore, while here the constants in the linear combination are given, they are 1, in the generalized version, we can tune the constants appearing in front of these conditional entropies to the desired values, provided they are non-negative and they satisfy the scaling condition. Okay, so here let me present the result. The results will be concerning this maximization problem that will give us the maximum of this function. So in the case of the strong subadditivity, this maximum is 0, but in the generic case, in this more general case, this maximum will not be zero. And here is what we have proved about that maximum. So first, this maximum actually does not depend on the dimension of the Hilbert space of the subsystem B. And actually, we can also choose B as the trivial quantum system. So even if B is not there and the entropies are not conditioned, the maximum does not change. And second, so the first simplification is that we can get rid of B and consider unconditioned entropies and the maximum will not change. And the second big simplification is that actually that maximum can be restricted to quantum Gaussian states of A. So the Gaussian states of a bosonic system are the quantum counterpart of the Gaussian probability distributions for vector valued random variables, and actually are the Gibbs states of the Hamiltonians that are quadratic in the quadratures. So here we have an enormous simplification because a maximum over all possible quantum states is restricted to a maximum over a very small family of states made by the Gaussian states. So moreover, we can actually express the maximization of this function here as a very simple maximization over positive definite real matrices. So here is like the main result that we have, that the supremum over the quantum states of the function that I showed you before can be expressed as a supremum over positive semi-definite, positive definite 2m times 2m real matrices. And here is the function that we can maximize rather than the original function. And it's a quite simple function. And I remind you that, okay, these PIs are the coefficients that appear in the linear combination. And these MIs are the matrices that define the subsystems that appear in the quantity to be maximized. Moreover, we have also shown that all the local optima, like all the local stationary point of this new function defined on matrices are actually global maxima for the function. So we can write the stationary point condition in this form. You can check it. And then we have proved that if some positive semi-definite matrix satisfies this stationary point condition for the function above, then this positive definite matrix is also a maximum point for the function. So this matrix alpha actually achieves the supremum in this equation. And if you want to connect this to which are the optimal quantum states that saturate this inequality, like that maximize this function here, we have also proved that if we have an alpha that is a stationary point of this function, then the supremum of the function of the quantum states is achieved by Gaussian quantum states that have like in the limit of an infinite covariance matrix. And this infinite covariance matrix is actually proportional to this alpha, this matrix alpha, that is a stationary point for this function. Okay, so we have like more or less characterized how to compute in a finite time the supremum of the function I showed you above. And first, let me tell you that this result actually is like built on a series of previous results that are both in the classical and in the quantum setting. Because, like, first of all, a similar generalization of the strong subadditivity of the classical Shannon differential entropy had been proved in the 90s by Elliott-Lieb, like in the classical case, for classical random variables that takes values in real vectors. And in the quantum setting, like similar inequalities had been proved, like first in the fermionic case, so for fermionic quantum systems by Eric Carland and Elliott-Lieb in 2008. And this version for bosonic quantum systems is the generalization of like some similar inequality that was proved by Berta, Sutter, and Walter, and was actually presented last year at Beyond IID. And like this inequality like concerns like the simpler case where the entropies have not like where there is no condition in quantum systems, so where the entropies are conditioned, and when the subsystems have like a particular form. And in this form, the matrices Mi that define the subsystems like do not mix position and momenta, and satisfy some technical geometric condition. So like this is a particular case of the inequality I just showed you that computes the maximum of this function. And here we have generalized that inequality for boson in the setup of bosonic quantum system in the most possible general case, in the most general possible case, where these subsystems are completely generic without any restriction. Okay, so we have proved this new inequality. Let me say a few words about possible applications. Like first, let us consider the case where all the subsystems are classical. So if all the subsystems are classical, this inequality provides a generalization of entropic uncertainty relations. In particular, it's a generalization of this entropic uncertainty relation proved by Frank and Lieb in 2013. So here we have a bosonic system, and we consider like bosonic system A conditioning quantum system B, and we consider the sum of the entropies of the position and the momentum of the system conditioned on B, and Frank and Lieb proved that the sum is larger or equal than the entropy of the system A conditioned on B. So this is an entropic uncertainty relation because it provides a lower bound to a sum of entropies of the output of measurements performed on the system, in this case, position and momentum. So how do we define the entropy of like random variable conditioned on a quantum system? More or less, we reverse the conditioning. So in general, the entropy of a random variable X conditioned on a quantum system B, we define it as the entropy of the quantum system B conditioned on the value of X, plus the entropy of X minus the entropy of the quantum system B, where the entropy of a quantum system conditioned on the random variable is equal to the average of the entropy of the quantum system conditioned on the possible values of the random variable. And the entropy of a random variable is just the Shannon differential entropy, that is minus the integral of the probability density times the logarithm of the probability density of the random variable. And actually, when all the subsystems that appear here are classical, this inequality provides a generalization of that inequality in the sense that provides a lower bound to this linear combination of the entropies of the outcome of measurements conditioned on the external quantum system B. Then the second application is entanglement generation. So this inequality provides a lower bound to the generation of correlations and entanglement induced by some Gaussian unitary operation of the system. So now we consider a bipartite bosonic quantum system A1, A2, and we apply some Gaussian unitary operation, and we call A prime equals to A1 prime, A2 prime, the system after the application of this Gaussian unitary operation, that is just some symplectic linear redefinition of the quadratures. And then if we write the sum of the mutual information between between the two subsystems before and after the application of the unitary, we can check that this is a quantity of the form of the same form that appeared that we have appeared in the inequality we have just proved. So here we have some like a linear combination of entropies of subsystems minus the entropy of the total system. And then our inequality provides a lower bound to this quantity, and this is a lower bound to the generation of mutual information by a unitary. And when the initial state is pure, this is a lower bound to the generation of entanglement. And actually, I have to add that, okay, in general, we have to perform by hand the maximization over covariance matrices, the one that I have shown here. But in the case where the symplectic matrix that's associated to the Gaussian unitary operation is actually symmetric, we can actually find an analytical expression for this optimization. And if we block partition the symplectic matrix in this way, actually the analytical expression for this lower bound will be the logarithm of the determinant of the upper left block times the determinant of the lower right block. So in this case, we have an explicit analytical bound for the generation of, in general, of mutual information, of correlations, and for pure states for the generation of entanglement. And actually, we have applied this result to this lower bound to the generation of entanglement to time evolutions induced by quadratic Hamiltonians. So here we look at the asymptotic case of the infinite time limit. We always consider a bipartite bosonic quantum system, A made of A1, A2. And then we consider a generic arbitrary initial state, and we consider the squashed entanglement between these two subregions and how the squashed entanglement scales with time, where the system is evolved with this time-independent generic quadratic Hamiltonian. And what we have proved is that the squashed entanglement of this joint system grows linearly with time with this prefactor lambda. And the fundamental property of lambda is that lambda depends only on the choice of the bipartition and on the Hamiltonian, but lambda is the same for every initial state. So the asymptotic behavior of the squash entanglement with respect to the time evolution induced by a quadratic Hamiltonian does not depend on the initial state of the system. Like we can choose it in any way. It can be mixed, pure, Gaussian, non-Gaussian, heavily entangled, or product. And for infinite time, the asymptotic behavior of the entanglement will always be the same. And actually, this is a generalization of a result that had previously proved by Bianchi, Hackl, and Giacomo a few years ago in the particular case of pure Gaussian initial states. So this, our result generalizes this to arbitrary initial states. Okay, and let me remind you how this quotient entanglement is defined. This quotient entanglement of a bipartite state is the minimum quantum conditional mutual information minimized over the extensions of the state. So we have a bipartite state on a system A1, A2. we consider all the extensions of this state on a third condition in quantum system B that have the same marginal of our given state on A1, A2. And then we minimize half of the mutual information between A1 and A2 conditioned on B. Okay, so now I can come to the conclusion. We have proved a generalization of the strong subadditivity inequality for the von Neumann entropy that applies to bosonic quantum systems and applies to generic subsystems. So the subsystems do not need any longer to be disjoint, and their union does not need to be the global system. And we, as applications, we presented finding new entropic uncertainty relation for the measurement of quadratures, and having a lower bound, proving lower bounds on the generation of entanglement in bipartite bosonic quantum systems with Gaussian unitary operations. So here are the references for this talk. Like the first paper is the proof of this generalized strong subadditivity. And the second paper contains the asymptotic scaling of the entanglement for bosonic quantum systems with respect to quadratic Hamiltonians. So that's all. Thanks for attention.
Thanks, Giacomo, for a very nice presentation. Is there any question for Giacomo? Okay, actually, I have one. So this subadditivity of entropy is related to this Braskamp leap inequality in the classical case. And here you're achieving this entropy inequality. Do you have some LP norm inequality as its dual form?
Yes, like I didn't have the time to talk about this in this presentation, but actually there will be there is this has been proved in this paper by Berta, Sutter, and Walter that any inequality like this for the entropy, like an upper bound to a quantity like this, always implies a corresponding dual trace inequalities that will contain of like this it will depend on the quantum channels that produce the marginal states of this subsystem given the original system. And like I did not talk about this dual inequality in the presentation because so far we have not found applications of this dual inequality that cannot be found directly from these entropic inequalities, but the dual inequality will definitely be there.
Okay, yeah. So I know this duality, but I'm interested in can you get some form of this the Young inequality in the setting? Like you have the Gaussian optimality for your entropy inequality. Is there a way that this can imply some hint for the Young inequality?
Okay, I think we looked at we were hoping that from this inequality, Young inequality for the Gaussian system would look something like we look at the P norm of the output of a bin splitter divide with a product input state divided by product of Q norm and R norm of the two inputs. In the same way as the Young inequality for convolutions would be an upper bound to the ratio of the LP norm of a convolution divided by Q norm of first function times R norm of second function. We were hoping that this kind of inequalities will lead to the generalization of Young for the bin splitter, but it is actually it is not these inequalities are not enough to prove that inequality so far.
Okay.
So it's something that we believe, like, we conjecture that that's still optimized by Gaussian states, but we do not have a proof yet.
Okay. Yeah. Thanks for the answers. Is there any other questions for Giacomo? Okay, if no, this is the end of the first session. Let's thank Giacomo and all our three speakers again. And thank you for attending. I think the next session will resume in 18 minutes, about 18 minutes.